Yeah.
I'll do this when we get to the procedure.
Okay, we did our lab on the compression of clay based on temperature and gravitational potential energy. The purpose of this lab was to find out how the gravitational potential energy is related to the compression of clay. Because we thought that was a little bit easy, we decided to throw temperature into the mix to see how that affected it. Our hypothesis was we figured that when clay at a higher temperature, it would compress more, and because obviously the molecules would be spread apart more, so we figured that it would compress a lot more. We thought that GPE was gravitational potential energy would be related to compression. We assumed that at higher gravitational potentials, it would have a higher compression. The equipment we used clay, which Owen is holding right now. We used meter stick and all this stuff to measure the height. And we used an infrared thermometer to take the temperature. Because we couldn't really keep the temperature completely constant when we warmed it up, because it's not perfect, because it's going to lose a lot when we're rubbing, when I'm holding with my hands, and it'll just go into the air, so we just took an average of that. So this is our procedure.
So basically we just drop the clay like this. As you can see, it doesn't bounce at all. So we figured that meant that all of the gravitational potential energy went into the compression of the clay. And then we just measured, we would have a perfect sphere when we were doing the experiment. This is not
as close as we could
as close as you can make it. But we measured the compression of, the height. We call it diameter in the experiment.
Yeah.
Oh. Okay.
Yeah, we measured the circle at the bottom of that too, because we thought that would have something to do with it. It didn't really have too much to do with it. And the way we warmed it up was we actually put it in a Ziploc bag and ran it underwater to try to get it as evenly spread out as possible. And it worked, just it lost its heat pretty quickly, so we averaged that.
So this is when we heated it up. It's the gravitational potential, the compression versus the gravitational potential energy. And as you can see, it looks kind of wonky because we did a proportional fit instead of a linear fit. And that's because I figured if you just set the clay down and drop it from a height of 0, it's not going to compress at all. So it has to go through the origin. And the reason it's not on the line and it's skewed like that is because when we did the first trials, it was much hotter than we did the final trial. So there was a lot of error, and it made it look like the slope was less than it should have been.
Yeah, just to make this clear, just 28.9 was the average of the two temperatures.
Yeah, we took the average of the beginning temperature and the end temperature.
Were the hotter experiments always done first and from lower heights?
We kept all the heights constant.
Wait, go back to the previous graph, please. That represents several heights, right?
Yes. These are
Were the hotter
heights.
ones always the earlier heights, the lower heights?
What do you mean by that?
You said the temperature was changing while you were doing the experiments.
You did,
Yeah.
we did them in order from lowest to...
Yeah, I started with 1 meter, and I went to 1.5, then 1.8, then 2, and then 2.3. I did it progressive.
So regrettably, the temperature was changing while the height was also changing.
Yeah.
How long would you estimate it took for you to get from the first drop to the last drop?
It took about maybe 2-3 minutes.
Okay.
It was as quick as I could do it.
Okay.
Being one person.
So this is the one at room temperature, and as you can see, it works a lot better with the fit.
Yeah, because I tried to touch it the least amount as possible, so I
One
didn't
outlying point.
change the heat.
And this is the cooler one. It didn't have as much error, but other than the first point, it does. The slope looked like it could have been a little bit higher if we did have done a linear fit. And this is our final graph, which is the energy coefficient of compression, which is the slope. We took the slope of those 3 graphs and called it the energy coefficient of compression, and then we graphed that versus the temperature.
It had a pretty good correlation.
Yeah.
It had almost 1-to-1 correlation.
I think maybe we should have done a proportional fit on that one too.
Yeah.
Maybe not
We did.
actually.
It wouldn't.
Makes sense.
It wouldn't change much. It does
Yeah.
look really.
It's pretty. And this is the equation we came up with by using our energy coefficient that we got from that graph. This was the slope,
So
which we said
We,
was C.
yeah, we made C, which is basically the inherent squishiness of the material, because we took out the mass of the ball, G, the height that we dropped it from, and the temperature. So C was the squishiness of the material, and if you use that equation, then you can get that should be change in.
Yeah, that should be changed in T, not
It didn't carry over when I copied and pasted it into the thing.
So, yeah, and this is just for this specific situation. Obviously, we don't think this will work in every circumstance. but
Probably will only work for around room temperature, because
when room temperature is what it's surrounded in and the clay.
and I was thinking if that last graph, if you maybe go back. The last graph, if it was really linear, then eventually it would be negative, and that doesn't really make sense. Because if you dropped really cold clay, it wouldn't expand when it hit the ground.
Yeah.
So this probably really only works for a very narrow room temperature window.
But this works for our experiment,
Yeah.
at the very least. And that is everything.
Thank you, gentlemen. We have time for a question.
Ooh.
Yeah.
You might have just answered this in the last little bit that you said, but did you make an active decision to keep it around room temperature rather than like do a wider range of temperatures? Like,
Well, we just had room temperature as what was surrounding the clay is what we changed the temperature of, because
Right.
we didn't feel like doing it in different rooms, because that could, the heat transfer between the clay and the room, the air in the room would just make it even more wonky than it already is. 'cause
right?
it's already-
I'm just asking like why you decided to use a smaller range? Like you heated it with the water, so you got like a
Time.
6, 7, 8 degree Celsius range. But you could have why did you choose not to use like ice and like fire? So like,
Fire.
Yeah.
so, like,
That's practical.
More labs with fire.
For the sake of time
Yeah.
and just getting it done.
okay.
Ellie?
In that equation that you have right there, what does D represent?
D, that's the
Diameter.
change in diameter.
Should have been
Sorry.
Oh,
D,
okay.
but it-
Yeah, that
got it
didn't
wrong.
go into the presentation.
Delta D would have tongue
Alright.
twisted.
And that's not of the circle at the bottom, that's of like the
That's
whole
of
sphere?
the diameter of the sphere, or as close as we can get. So that's part of the error, because it's not a perfect sphere, because,
Mhm.
well, we didn't make a mold.
Okay.
Brett?
Could you guys have heated up the clay for each experiment? That way you wouldn't have lost the heat.
It's sort of difficult to get it to the same temperature each time, because we were just using water.
It's hard to be exact.
In their defense, they had a different lab planned, and everything fell apart for various reasons on that lab. And
Yeah.
this was done the day before, desperately.
Yeah.
All right, thank you, gentlemen.